Close your eyes for a moment and picture the universe exactly as it is right now. In one distant region, a new star is forming within a quiet cloud of gas and dust, its light not yet visible to any watching eyes. In another direction, ancient light from a faraway galaxy is just now reaching the mirror of a telescope after traveling for billions of years across the darkness. And somewhere in the immeasurable depth of space, in ways we still cannot directly sense, the universe is slowly and gently moving toward its distant future. This is not a frightening idea. There is something deeply calming about thinking of endings on such an immense scale that they feel soft and abstract, distant not only in space, but in stretches of time so vast that the human mind can barely brush against their edges. As far as we can tell, the universe had a beginning, and like all things that begin, it will in some manner also come to an end. But what does it truly mean for a universe to end? How does something so immense, so astonishingly large, containing hundreds of billions of galaxies, and within each of them hundreds of billions of stars, ever reach a conclusion? This is one of the deepest questions in cosmology, and the possibilities scientists explore are as rich as they are awe-inspiring. We are living in an extraordinary era. For most of human history, the fate of the universe belonged to myth, philosophy, and spiritual imagination. Only in the last century, and especially in recent decades, have we gained the mathematical insight and observational tools to explore this question scientifically. We can look back to a time very close to the beginning, to a fraction of a second after the Big Bang. We can measure how fast space is expanding. We can observe the subtle influence of dark matter and the even more mysterious presence of dark energy. From this growing body of evidence, we build models, careful theories, and thoughtful predictions about the ultimate fate of everything we know. Tonight, as your body relaxes and your thoughts drift gently through these vast ideas, we will move through several different visions of how the universe might end. Some are grounded in well-tested physics, supported by observations and equations that have proven reliable again and again. Others are more speculative, reaching into regions where our knowledge becomes thin and our understanding blends into possibility. We will encounter the idea of a slow fading known as heat death, where the universe gradually reaches a state of maximum entropy and quiet stillness. We will consider the Big Rip, where the expansion of space accelerates so dramatically that galaxies, stars, planets, and eventually atoms themselves are pulled apart. We will reflect on the Big Crunch, a reversal in which cosmic expansion halts and all matter falls back together. And we will also wander into more exotic territory, imagining universes that collapse and are reborn in endless cycles, or the sudden transformation of all existence through a process called vacuum decay. Each scenario teaches us something not only about physics, but about the nature of reality and change. They invite us to think about time on scales that far exceed everyday experience. A human life lasts decades. Civilizations rise and fall over centuries and thousands of years. But the futures we are exploring unfold across trillions, quadrillions, or even greater spans of time. When we allow our minds to stretch towards such immensity, something interesting happens. The urgency of daily worry softens. We gain a perspective that is both humbling and quietly comforting. There is also a deep beauty in the realization that the universe, for all its grandeur and complexity, is not fixed forever in one unchanging state. Everything moves. Everything transforms. From the smallest quantum fluctuation to the largest clusters of galaxies, all things exist within time, and time means change. The universe a billion years ago was not the same as the one we see today, and the universe a billion years from now will be different again. This impermanence is not a flaw in existence. It is what allows anything to happen at all. Without change, there would be no stars igniting, no planets forming, no life emerging, no thoughts arising to wonder about the sky. So as we explore these possible endings, there is no need for fear. We are simply acknowledging the natural flow of a universe that lives in time. And in a cosmos that will not last forever, the present moment becomes even more precious. The fact that you are here now, aware and able to reflect on these immense ideas, is itself something extraordinary. You are a temporary pattern of matter and energy that has become conscious, if only for a brief moment in cosmic history. Let your breathing grow slower and softer. Allow your body to settle into comfort. And together, let us begin this gentle journey into the ways all things might one day come to rest. Before we can truly sense how the universe may end, it helps to appreciate the strange and beautiful nature of cosmic time. In daily life, we experience time in a familiar way. Seconds pass on a clock, days turn into weeks, years accumulate as we grow older. But cosmic time unfolds on scales so enormous that our usual intuition must stretch far beyond its comfort. The universe is about 13.8 billion years old. Written in full, that is 13,800 million years. Every human who has ever lived, every culture that has flourished, every story told, every monument built and worn down by weather, all of this has taken place in a tiny recent fraction of cosmic history. We are very new arrivals in a very old universe. And yet, even 13.8 billion years is brief compared with the timescales over which the universe may approach its end. Numbers of this size slip beyond ordinary imagination. If you try to count one number every second without stopping, you would never come close. Time at this scale loses the rhythms we associate with life. There are no familiar cycles of seasons, no days and nights, no generations rising and passing. Instead, there is the slow unfolding of physical processes guided by steady laws that operate with quiet consistency. Space itself is just as surprising. We often picture space as an empty stage where events take place, but modern physics reveals something far more dynamic. Space and time are woven together into a single fabric called space-time. This fabric can bend in the presence of mass and energy, shaping the motion of planets, stars, and galaxies. Even more astonishing, space-time itself can expand. At this very moment, the universe is growing larger. This discovery changed cosmology forever. In the early 20th century, astronomers observed that distant galaxies are moving away from us, and that the more distant a galaxy is, the faster it appears to recede. This does not mean galaxies are racing through space in the usual sense. Instead, the space between galaxies is stretching, like dots on the surface of a balloon that is slowly inflating. For many years, scientists expected that this expansion would gradually slow down under the pull of gravity. But toward the end of the 20th century, observations of distant, exploding stars revealed a surprise. The expansion is speeding up. Galaxies are separating from one another at an ever-increasing rate. This acceleration is linked to something we call dark energy, a mysterious component that fills space and gently drives it to expand faster over time. We still do not know what dark energy truly is. It might be an inherent property of space itself, similar to a cosmological constant. Or it might be something that evolves slowly as the universe ages. This uncertainty is one of the key reasons we cannot yet say with complete confidence how everything will end. The future of the cosmos depends strongly on how dark energy behaves across unimaginable stretches of time. There is a quiet, almost meditative quality in reflecting on cosmic expansion. Even now, as you rest and breathe, the universe is growing. Distances between faraway galaxies increase, not because they're traveling through space in a conventional way, but because the fabric of reality itself is gently stretching. In the time it takes you to take a calm breath, space on the largest scales expands by enormous distances. And yet nothing in your immediate surroundings seems to change. The space inside your body, inside the Earth, and inside our galaxy does not noticeably expand because local forces hold these structures together far more strongly than the subtle stretching of cosmic space. This is the kind of universe we inhabit. It is vast beyond ordinary comprehension, expanding steadily and evolving over timescales that make human history seem like a fleeting instant. When we speak of the universe ending, we're talking about processes that unfold across these immense spans, guided always by the same fundamental laws of physics. The universe is not a fixed backdrop. It is an active participant in its own story, changing, growing, and transforming. And those same laws that allow stars to shine and life to emerge also suggest that change never truly stops. The cosmos we see today will not remain as it is forever. It will continue to evolve into forms so unfamiliar that we can barely picture them. Still, we can try. And in the act of trying, in allowing our imagination to travel across these cosmic distances of time and space, we touch something profound. We sense our place within a vast, unfolding story, brief and delicate, yet undeniably real. With this wider view in mind, we are ready to explore the first of the great possibilities for the universe's distant future, one of the most scientifically grounded and quietly moving visions of all, the slow fading known as the heat death of the universe, where everything gradually drifts into darkness and deep stillness. There is a principle in physics known as the second law of thermodynamics, which tells us that entropy, a measure of disorder or randomness, tends to increase over time in a closed system. This is why a cup of hot coffee cools as it sits on a table, why the scent of perfume spreads through a room, and why physical structures slowly wear down and fall apart. Energy naturally spreads out. Differences in temperature and structure gradually even out. If the universe as a whole is a closed system, as most physicists believe, then this quiet rule applies not just to kitchens and laboratories, but to the entire cosmos. The long-term consequence of ever-increasing entropy is something called the heat death of the universe. Despite the name, this is not about burning heat or fiery destruction. It describes a gradual leveling out of all energy differences. In a state of maximum entropy, there are no temperature contrasts, no usable energy gradients, nothing left to power motion or change. Everything approaches the same faint temperature, only a tiny bit above absolute zero. When no differences remain, no work can be done and no meaningful processes can occur. The universe does not explode or collapse in this vision. It simply grows quieter and more still, like a vast system gently winding down. This may sound sad, and in a way it is, but it is also peaceful. Imagine the universe not ending in catastrophe, but slowly settling, like a spinning top that turns more and more slowly until it finally rests. Let us move through this future step by step, across spans of time so enormous that the current age of the universe feels like a brief flicker. Right now, we live in what scientists call the stelliferous era, the age of stars. This period began a few 100 million years after the Big Bang, when the first stars ignited, and it will continue for many trillions of years to come. Yet it is not endless. Stars are born from clouds of hydrogen and helium. Over time, more of this gas becomes locked inside stars, fused into heavier elements, or blown away into space. Gradually, the raw material for new stars runs low. The smallest stars, known as red dwarfs, use their fuel very slowly. A red dwarf can shine for 10 trillion years or more, far longer than the universe has existed so far. But even these long-lived stars will one day exhaust their fuel and fade. By roughly 100 trillion years from now, the last true stars will burn out, and the universe will enter a long era of darkness. Yet even then, the story is not completely finished. In that deep night, there will still be stellar remnants. White dwarfs, which are the cooling cores of dead stars, will drift through space. Neutron stars, incredibly dense objects formed from collapsed stellar cores, will remain. Black holes, where gravity is so strong that not even light can escape, will persist as well. These objects seem almost eternal on human timescales, but on the largest scales, even they are temporary. White dwarfs are made mostly of carbon and oxygen packed into a crystal-like structure, and they cool ever more slowly toward absolute zero. Over unbelievably long periods, possibly around 10 to the power of 32 years or more, some theories suggest that the protons inside atomic nuclei may decay. Proton decay has never been observed, but many extensions of particle physics predict that protons are not perfectly stable, only extremely long-lived. If this is true, then all ordinary matter, every atom in white dwarfs, neutron stars, and scattered debris, will eventually break down into lighter particles and radiation. The numbers involved are staggering. Experiments tell us that if protons decay at all, their half-life must be at least 10 to the power of 34 years. Compare this with the current age of the universe, about 10 to the power of 10 years. We are speaking of times a trillion times longer than everything that has happened so far. Imagine observing the universe only once every trillion years. It would seem almost unchanged each time. But if you could watch across the full span of 10 to the power of 34 years, you would see matter itself slowly dissolving. Atoms would fall apart as protons transform into lighter particles such as positrons, neutrinos, and photons, which drift away into the growing emptiness. What about black holes, once thought to be the ultimate permanent objects? In the 1970s, Stephen Hawking showed that black holes are not completely black. Because of quantum effects near their boundaries, they emit a very faint glow now called Hawking radiation. This means black holes slowly lose mass and can eventually evaporate. The larger the black hole, the slower this process. A black hole with the mass of our sun would take about 10 to the power of 67 years to disappear. The supermassive black holes at the centers of galaxies, millions or billions of times heavier than the sun, would take even longer, perhaps 10 to the power of 100 years or more. Picture the far future, a time so distant that even the decay of protons lies in the past. The stars are gone. Solid matter has mostly disintegrated. All that remain are black holes, scattered through an enormous, dark universe. Very slowly, they radiate away their mass, shrinking over unimaginable spans of time. One by one, they fade in tiny flashes of radiation and then vanish after the last black hole evaporates. the universe becomes extremely simple. It may contain only very low energy photons and perhaps lightweight particles like neutrinos, spread incredibly thin by the continuing expansion of space. Their wavelengths stretch longer and longer until the universe is effectively a cold, dark, dilute expanse where almost nothing happens. Yet even here, there is a final strange twist. Quantum mechanics tells us that empty space is never truly empty. Tiny fluctuations constantly occur, with particles and antiparticles briefly appearing and disappearing. Most of these events are fleeting and insignificant, but given endless time and vast space, even very unlikely arrangements can occur by chance. Some physicists have suggested that in the remote future rare quantum fluctuations might create small pockets of temporary order, perhaps even something like a self-aware structure, sometimes called a Boltzmann brain. These hypothetical observers would arise momentarily out of randomness and then dissolve again. It is an odd idea, a little unsettling, yet also a reminder that at the deepest level reality never becomes perfectly still. There is always a faint trembling of possibility. The heat death has no dramatic final scene. There is no single moment when everything stops. Instead, the universe grows ever more diffuse, ever colder, ever darker, until change becomes so rare and spread out that time itself loses its usual meaning. After all, if nothing happens, what does it mean to say that time passes? And yet there is a quiet serenity in this picture. The universe does not struggle against its fate. It follows the general direction set by thermodynamics, moving toward equilibrium the way water flows downhill. Complexity slowly relaxes back into simplicity. For us, living in a bright and active cosmic era, this destiny is unimaginably far away. The difference between 1,000,000 years and 1,000,000,000 years is trivial compared with what lies ahead. Still, reflecting on this possible future can bring perspective. It reminds us that everything is temporary, even the stars and galaxies. And perhaps it is precisely this impermanence that gives the present its vividness. Rest for a moment with the image of a universe gradually dimming, cooling, and quieting, not in fear, but in a long, peaceful sigh. Now let that vision fade gently, and we will turn to a very different possibility, one in which the universe does not slowly fade, but instead is pulled apart in a dramatic finale known as the Big Rip. In this scenario, the same dark energy that currently drives cosmic acceleration grows stronger over time. At present, dark energy makes up most of the energy content of the universe, roughly 2/3 of the total. We see its influence in the way the expansion of space speeds up, yet we do not know its true nature. Many models assume its density stays constant as space expands, meaning more dark energy appears as more space comes into being. This fits present observations. But imagine that dark energy is not constant. Imagine its influence slowly increasing. Physicists sometimes call this hypothetical behavior phantom energy. If such a component exists, the future of the cosmos changes dramatically. Expansion would not just accelerate, it would accelerate faster and faster. The rate of expansion would grow without bound. Eventually, this stretching of space would overpower the forces that hold structures together. The largest systems would be affected first. Galaxy clusters bound by gravity would drift apart. Then individual galaxies would lose their cohesion. Later, star systems would be disrupted. Planets would be torn from their stars. In the final moments, even atoms and the structure of space-time itself could be ripped apart. Let's imagine this future slowly approaching. For billions of years, little seems unusual. Galaxies continue to separate and stars are born and die. But the expansion rate creeps upward. Around 20 billion years from now, distant galaxy clusters slip beyond our observable horizon. Their light stretched and faded by the growing space between us. By 50 billion years, the acceleration is strong enough that galaxy clusters can no longer remain bound. Galaxies that once orbited together drift away from one another. Our local group of galaxies might remain intact for a while, but larger cosmic structures dissolve. As the final billion years approach, expansion becomes more dramatic. Even single galaxies struggle to stay together. Stars in the Milky Way drift apart. The Andromeda Galaxy, which would otherwise merge with ours, is instead pulled to pieces along with it. In the last million years before the end, solar systems unravel. Planets lose their orbits and wander into the darkness. The Earth, if it still exists, is drawn away from the Sun. The Moon is pulled from the Earth. Differences in the expansion across small distances create intense tidal forces. In the final months, these forces become strong enough to tear planets apart. Matter is stretched and scattered. The expansion rate grows so extreme that distances increase faster than light could cross them. Not because objects move through space that fast, but because space itself is stretching. In the last minutes, even atomic nuclei cannot hold together. The strong nuclear force is overwhelmed and atoms break into their component particles. Finally, in a last fraction of a second, the structure of space-time itself fails. The equations that describe reality reach a kind of future singularity. This is the Big Rip, a dramatic end where known physics can no longer guide us. What follows is unknown. Perhaps everything simply ends. Perhaps a new form of reality emerges. This boundary lies beyond our current understanding. It is important to remember that this is speculative. Observations so far suggest that if dark energy changes at all, it does so very gently. If a big rip ever occurs, it is likely at least 100 billion years away, and perhaps far more distant. Many physicists favor models where dark energy remains constant and the universe avoids this violent fate. Still, the idea teaches us something profound. Space is not just a passive background. It can stretch, curve, and evolve. And if its expansion becomes extreme enough, it can overcome every other force. In this scenario, nothing is exempt. From the largest galaxy cluster to the smallest particle, all structures eventually give way. Yet even here, there's a kind of pattern, a logic governed by the properties of dark energy. If such an ending occurred, it might possess a strange and terrible beauty, a final crescendo of expansion. For now, resting in this era where stars shine and galaxies hold together, we can feel safe. These possibilities lie unimaginably far ahead. Let the image of the Big Rip drift away like a distant dream, and prepare to explore yet another vision of the universe's deep future. In the earliest moments of cosmic history, according to our best understanding, the universe began in an extremely hot and dense state and then started to expand. This event, which we call the Big Bang, marked the beginning of space, time, and all the structure we see around us today. But expansion does not automatically mean forever. There is another possibility, one that is quieter in imagination, yet immense in scale. What if the outward journey of the universe is only half of a much larger cycle? What if, after ages beyond counting, gravity slowly regains control and begins to draw everything back inward? This potential future is known as the Big Crunch. For such a cosmic reversal to happen, The universe would need to contain enough matter and energy for gravity to eventually overcome the expansion of space. A simple way to picture this is to imagine throwing a ball upward from the surface of the Earth. If the ball is thrown with enough speed, it escapes gravity and never returns. If it is thrown more gently, it rises, slows, pauses for a brief instant, and then falls back down. In a similar way, the universe may have expanded with a certain cosmic momentum. If that momentum is not strong enough to last forever, then expansion could gradually slow, come to a stop, and gently reverse into contraction. For a long time, this was considered one of the leading possibilities for the fate of the cosmos. Before the discovery of dark energy, astronomers carefully measured how much matter existed in galaxies and in the vast spaces between them. The key question was whether the total density of the universe was above or below a critical value. If it was above that value, gravity would eventually halt expansion and pull everything back together. If it was below, the universe would expand forever. This simple balance between expansion and gravity shaped decades of cosmological thought. Today, observations suggest that expansion is accelerating, driven by a mysterious component we call dark energy. This makes a big crunch seem unlikely based on what we currently know. Yet our understanding of dark energy is still incomplete. It could change over time, weaken, or behave in ways we have not yet discovered. So, in a calm and imaginative exploration of cosmic possibilities, we can still consider how a contracting universe might unfold. For billions or even trillions of years, life in the universe would appear completely ordinary. Galaxies would continue to drift apart for a long time. Stars would form, shine, and fade. Planets would orbit, and cosmic processes would continue their slow and majestic rhythm. Then so gradually that no single observer could notice within a lifetime, the expansion would begin to slow. The distances between galaxies would still grow, but less quickly than before. Eventually, in the deep future, the expansion would reach a moment of perfect balance. For an instant that stretches across cosmic scales, the universe would neither expand nor contract. Space would hold steady, like a breath gently paused. Then contraction would begin. At first, it would be incredibly subtle. Galaxies that had long been moving apart would start drifting toward one another, so slowly that the change would only be visible over millions of years. As contraction continues, its effects become clearer. Light traveling through space would be compressed rather than stretched. The faint background glow left over from the early universe, which has been cooling for billions of years, would begin to warm again. The night sky would slowly grow brighter as distant galaxies, once carried beyond view by expansion, return into the observable cosmos. Over immense spans of time, gravity would pull structures closer together. Galaxies would collide and merge more frequently, forming larger and larger systems. The vast cosmic web of galaxy clusters and filaments would tighten. Space itself would be shrinking, and with that shrinkage, the overall temperature of the universe would begin to rise. At first, this warming would be gentle, almost unnoticeable compared to the heat of stars. But as the universe becomes smaller and denser, the background radiation would grow stronger. Stars, which normally release energy into the cold darkness around them, would find themselves surrounded by an environment that is slowly heating up. Shedding heat would become more difficult. In time, the universe would grow so warm that stars could no longer remain stable. Instead of shining as bright points in a dark sky, they would be immersed in a glowing cosmic background. Gradually, stellar structures would break down, their material blending into the surrounding hot plasma. The distinction between individual stars and the space between them would begin to fade. As contraction continues, matter would be compressed into ever smaller volumes. Galaxies would lose their separate identities, merging into one vast ocean of particles and radiation. Atoms would not be able to survive under such conditions. Their electrons would be stripped away, leaving bare nuclei. As temperatures rise further, even atomic nuclei would break apart into their fundamental particles. The universe would become simpler as it becomes denser. Complex structures that once took billions of years to form would dissolve. Distances that once separated galaxies by millions of light years would shrink to scales smaller than solar systems, then smaller than planets, then far smaller than anything familiar. The entire cosmos would be moving toward a state of extreme heat and density, echoing the conditions believed to exist at the beginning of time. In the final stages of this contraction, the universe might compress into a region so small and dense that our current physical theories can no longer describe it clearly. General relativity predicts a singular state of infinite density and temperature, but we know this cannot be the full story. At such tiny scales, quantum effects become essential, and we do not yet have a complete theory that unites gravity with quantum physics. Some scientists imagine that this extreme state would not be a final ending, but a transition. The collapse of one universe might trigger the birth of another expanding phase. In this picture, a big crunch could lead naturally into a new Big Bang, forming a cycle that repeats over unimaginable stretches of time. Each universe could be one chapter in a much larger cosmic story. There's a deep symmetry in this vision. The universe expands from a hot, dense beginning into complexity and structure, and after ages beyond comprehension, it returns toward simplicity and density once more. It is like a vast cosmic rhythm, an outward movement followed by a gentle return inward. Even in such a contracting universe, time would still feel as though it flows forward for any observers who might exist. Events would follow one another in sequence. Memories would still point toward the past. The arrow of time, linked to the growth of entropy, would likely continue even as space itself shrinks. Although present evidence suggests our universe will probably keep expanding, the Big Crunch remains a meaningful and beautiful possibility to contemplate. It reminds us that cosmic history may be more like a cycle than a straight line, more like a breathing motion than a single, endless expansion. And as you rest and imagine this slow return of everything toward a shared center, the present moment can feel softer and more precious. There's a very old idea, appearing in Hindu cosmology, in strands of Greek philosophy, and in other ancient traditions, that the universe is eternal not because it remains the same forever, but because it moves through endless cycles of creation and destruction. In this view, existence is not a straight line with a single beginning and a final end, but a great repeating rhythm. Modern physics, in a quiet and surprising way, has breathed new life into this ancient intuition through several theoretical models that suggest our universe could be just one phase in an ongoing sequence of cosmic rebirths, a vast cycle of expansion and contraction often described through ideas like the Big Bang, the Big Crunch, and the Big Bounce. One of the simplest versions of this picture is known as the oscillating universe. Imagine that the cosmic contraction we spoke about earlier does not end in a final state where everything is crushed into an unreachable singular point. Instead, picture the universe shrinking to a very small size and then gently reversing, expanding once again in a new Big Bang. This new universe would grow, form stars and galaxies, slowly age, and eventually contract into another dense state, only to bounce once more. In this calm and repeating vision, our universe is just one chapter in an infinite cosmic story, one breath in an endless pattern of breathing in and breathing out. Naturally, this leads to a deep question. What could stop a collapsing universe from forming a singularity in the first place? The answer may lie in the still, mysterious realm of quantum gravity. At extremely tiny scales and enormous energies, the familiar laws of gravity described by Einstein begin to blend with the strange rules of quantum physics. Although scientists do not yet have a complete and final theory of quantum gravity, several leading approaches suggest that quantum effects could prevent matter and space from being compressed into an infinitely dense point. One such approach is called loop quantum cosmology. This theory grows out of loop quantum gravity and applies its ideas to the universe as a whole. In this framework, space and time are not perfectly smooth and continuous. Instead, at the smallest scales, space-time has a kind of discrete structure, almost like a fine fabric woven from tiny threads. This structure becomes important when the universe contracts to incredibly small sizes, close to what physicists call the Planck scale, the smallest meaningful scale in nature. According to calculations in loop quantum cosmology, as the universe shrinks and its density rises toward this extreme regime, quantum gravitational effects create a strong repulsive influence. Rather than allowing collapse to continue without limit, this effect halts the contraction and turns it around. The universe rebounds and begins expanding again. In this picture, what we call the Big Bang is not an absolute beginning, but a big bounce, a transition from a previous contracting phase into the expanding universe we now observe. One of the most intriguing aspects of this scenario is that a bounce might not completely erase the past. Depending on the details of the physics, certain large-scale patterns could pass through the bounce and leave faint traces in the next cycle. Our universe might carry subtle imprints from an earlier cosmic era, possibly encoded in delicate features of the cosmic microwave background, the soft afterglow of the early universe that still fills space today. Another remarkable cyclic idea was proposed by the physicist Roger Penrose. His model, known as conformal cyclic cosmology, begins from a different observation. Penrose noticed a kind of mathematical similarity between the very early universe and the extremely distant future of an old universe. Near the beginning, the cosmos is hot, smooth, and dominated by radiation. In the unimaginably far future, after stars have burned out, particles have decayed, and black holes have slowly evaporated, the universe again becomes thin, smooth, and largely filled with radiation. Penrose showed that, through a mathematical reshaping called a conformal transformation, the infinite future of one cosmic era can be mapped onto the Big Bang of the next. In this framework, each long-lived universe is called an aeon. The remote future of one aeon flows naturally into the birth of another. Time stretches endlessly forward, and our universe is just one aeon in an eternal sequence. Penrose has suggested that certain circular patterns in the cosmic microwave background might be hints of events that took place in a previous aeon, although these claims remain debated and are not widely accepted. Cyclic models carry a deep emotional and philosophical appeal. They soften the sharp question of an absolute beginning. Instead of asking what happened before the Big Bang and meeting a wall where time itself seems to start, the cyclic view answers gently that there was another universe before this one, and another before that, extending without beginning into the past. These ideas also echo the rhythms we see everywhere in nature. The cycle of day and night, the turning of the seasons, the life and death of stars, whose material later forms new stars and planets. Even our own breathing follows a cycle, in and out, again and again. It feels almost natural to imagine that the universe itself might follow a similar grand rhythm. Yet cyclic cosmology also opens profound questions. If the universe has repeated forever, why does this particular cycle seem so finely balanced in a way that allows galaxies, stars, planets, and life to exist? If each cycle is not exactly the same, what sets the differences between them? And on a more personal and philosophical level, if everything happens again and again, does that change the meaning we attach to a single life or a single moment? Some scientists have explored the possibility that each cycle might have slightly different physical constants. The strength of gravity, the masses of fundamental particles, or other basic properties might vary a little from one cosmic era to the next. In that case, our universe would not be unique in an absolute sense, but it would be one of the rare cycles where the conditions happen to support complex structures and living beings. There are also cyclic scenarios inspired by string theory and higher dimensional physics. In these models, our visible universe is like a three-dimensional surface, sometimes called a brane, floating in a space with extra dimensions. Other branes could exist nearby in this higher dimensional setting. From time to time, these branes might drift together and collide. Such a collision would release tremendous energy, heating the universe and creating conditions much like a Big Bang, beginning a new cycle of cosmic evolution. In these brane collision pictures, the long period between collisions is the era we now inhabit, a time when the universe expands, cools, and forms structure. After trillions of years, another encounter could occur, flooding the cosmos with energy and starting the cycle anew. Time, in a larger sense, would stretch endlessly into both past and future, while our familiar cosmic history would be just one repeating phase. One of the most beautiful features of certain cyclic models is that they remove the idea of a final ending. There is no ultimate heat death that lasts forever, no permanent tearing apart, no absolute collapse that ends the story. Instead, there are transitions, gentle or dramatic changes from one state to another, while the cosmos as a whole continues without limit. This leads to a quietly mind-bending thought. In an eternal cyclic universe, every possible arrangement of matter and energy that can exist would exist not just once, but endlessly many times. The exact pattern that makes up you, your thoughts, your experiences, could arise again and again across the cycles. This resembles the ancient philosophical idea of eternal return, now framed in the language of modern cosmology. Some people find this deeply comforting, a sense that nothing is ever completely lost and that existence has an endless continuity. Others find it unsettling, as if nothing is ever truly finished and nothing is entirely new. Writers and thinkers have long played with such ideas, exploring the strange emotional weight of infinity and repetition. For now, it is important to rest in the understanding that cyclic cosmology remains speculative. We do not yet have direct observational proof that the universe bounces or repeats. Current measurements of dark energy and cosmic expansion suggest a future of continued growth rather than reversal. Still, the history of physics teaches us humility. The universe has surprised us before, and it may do so again. Whether the cosmos truly cycles or not, The idea of a big bounce offers a gentle lesson. What appears to be an ending from one point of view may be a beginning from another. Destruction and creation, death and birth, may be parts of a single, continuous transformation seen from different angles. As you relax and let your thoughts drift, imagine this vast rhythm of contraction and expansion, like a slow cosmic breathing, an eternal pulse that carries universes into being and then gathers them back in. Rest with that image for a moment, and then we will move toward a very different kind of cosmic possibility, not a gradual fading or a graceful cycle, but a sudden and dramatic change that could sweep across the universe at the speed of light. Our universe may feel solid and dependable, but at the deepest level, reality could be more fragile than it appears. Physicists have discovered that what we call empty space is not truly empty. It is filled with quantum fields, invisible structures that define how particles exist and how forces behave. These fields determine the very rules of nature. And it is possible that the state these fields are in right now is not the most stable state possible. This idea leads to one of the most dramatic scenarios ever imagined in modern physics, a process known as vacuum decay. In everyday life, systems naturally move toward lower energy and greater stability. A rock rolls downhill. A stretched rubber band snaps back. Water settles in the lowest place it can reach. These are simple examples of nature seeking a state of rest. But sometimes a system can appear stable while still having an even lower state it could fall into. This is called a metastable state. Imagine a ball resting in a shallow dip on a hillside. It looks stable, and it will stay there unless disturbed. But somewhere farther down the hill is a deeper valley, a more stable resting place. If the ball could somehow pass through the hill itself and reach that deeper valley, it would release energy as it moved to that lower state. According to some interpretations of quantum field theory, the vacuum of space may be like that ball. What we experience as the stable foundation of reality might actually be a temporary plateau. A deeper, more stable state could exist, separated from ours by an energy barrier. Classically, a system trapped in such a state would remain there forever. But quantum mechanics allows something extraordinary. Through a process called quantum tunneling, a system can move through an energy barrier rather than over it. This happens constantly for tiny particles. And in principle, it could also happen to the quantum fields that fill the entire universe. If a small region of space were to tunnel into this lower energy state, it would create what physicists call a bubble of true vacuum inside our false vacuum. This bubble would not remain small. The difference in energy between the two states would drive the bubble to expand outward at the speed of light. As the bubble expands, it would convert the old vacuum into the new one. And here is where the scenario becomes truly profound. Inside this new vacuum, the laws of physics could be completely different. The strengths of forces might change. Particle masses could shift. Atoms might no longer hold together. The chemistry that makes stars, planets, and living beings possible might simply not exist. Because the bubble wall would move at the speed of light, there would be no warning. No signal could reach us ahead of it. One moment, the universe would be as it is now. The next moment, the region we occupy would be part of this new state, governed by different physical rules. From our perspective, the transition would be instantaneous. Among all cosmic scenarios, this is the most sudden. There is no long fading, no gradual collapse, no stretching apart over trillions of years. It is a phase change in reality itself, like water suddenly freezing or boiling, but on a cosmic scale. Before this sounds too alarming, It helps to remember how uncertain and remote this possibility is. We do not know whether our vacuum is actually metastable. Measurements of fundamental particles, especially the Higgs boson, leave open the possibility, but the calculations are extremely sensitive and not yet definitive. Even if our vacuum is metastable, the probability of decay appears unimaginably small. The expected time for such an event could be vastly longer than the current age of the universe, longer than stars will shine, longer than galaxies will remain distinct. In practical terms, it is not a danger to worry about, but a window into how strange the quantum world truly is. There's also a strangely gentle aspect to this scenario. Because the transition would happen at light speed, there would be no experience of it. No pain, no fear, no final moment of awareness. Existence would simply shift from one state to another faster than any thought could form. Vacuum decay also reveals something deep about reality. The stability of everything we see is not guaranteed by a rigid cosmic rulebook. It may instead rest on probabilities, on delicate quantum balances that have held steady for billions of years. The stars above, the ground beneath, and even the atoms in your body may exist in their current form because a particular quantum transition has not happened. And yet, despite this underlying uncertainty, the universe has proven remarkably enduring. For nearly 14 billion years, cosmic structures have formed, evolved, and given rise to complexity and awareness. If our vacuum is metastable, it is an extraordinarily long-lived one. Some physicists imagine that in a much larger multiverse, vacuum decay might have happened in other regions, creating domains with entirely different laws of nature. We find ourselves in a region where stability has lasted long enough for galaxies and life to form. In that sense, our existence may be tied to this long stretch of quantum calm. Seen from another angle, vacuum decay is not destruction but transformation. Energy is not lost. It is released as the system moves to a deeper state of rest. From the perspective of physics, it is a transition toward greater stability, even if that stability cannot host the structures we know. As you rest with this idea, there's a quiet shift in perspective. Every uneventful second, every ordinary moment in which reality continues as usual, is a continuation of an immense run of cosmic stability. The universe is not only vast and ancient, it is also, in a subtle way, delicately balanced. Whether vacuum decay ever occurs or not, the possibility reminds us that the foundations of reality are dynamic, not fixed. The stage on which existence unfolds is itself part of the story, capable of change at the deepest level. And with that thought, we gently set aside this sudden and silent ending and allow our attention to move toward even more unusual possibilities, where the fate of the universe is tied not just to physics, but to the nature of reality itself. As we continue drifting through these deep possibilities about how everything might one day come to a close, we move into a realm where science softens at the edges and blends with philosophy, where equations meet imagination, and where certainty gives way to wonder. The ideas here are not firm predictions, and they are not claims about what will definitely happen. Instead, they are invitations to reflect, to let the mind open gently to possibilities that stretch far beyond everyday thinking. In this quiet exploration, the value is not in proving what is true, but in expanding what feels possible, in allowing your awareness to float through vast conceptual spaces the same way you might drift through a dream. One of the most captivating of these possibilities begins with a simple but profound question. What if our universe is not the most fundamental layer of reality? What if everything we see, every galaxy, every star, every breath you take, exists within an immense and intricate simulation? This idea, often called the simulation hypothesis, suggests that what we experience as physical reality could be more like an incredibly detailed virtual world generated by processes taking place in a deeper level of existence. Surprisingly, this concept is not limited to science fiction. Philosophers, physicists, and computer scientists have all taken it seriously enough to explore its implications. If our universe were a simulation, the question of how it ends takes on an entirely different meaning. The simplest possibility is also the most abrupt. The simulation could simply be switched off. From inside the system, there would be no warning, no gradual fading, no cosmic signal. One moment, everything exists. The next moment, nothing does. Not darkness, not emptiness, but a complete absence of experience because the process generating experience has stopped. Yet the ending of a simulation might not be so sudden or so simple. Simulations are usually created for reasons. Perhaps our universe is an experiment designed to explore how complexity emerges. Perhaps it is a reconstruction of a distant past. Perhaps it serves a purpose we cannot even begin to imagine. If so, the simulation might conclude when its goal is achieved. The data gathered, the scenario completed, the run finished. In that case, the end of the universe would not be a physical catastrophe, but the closing of a program after its purpose has been fulfilled. There is also the possibility that the simulation does not run only once. It might operate in cycles, restarted again and again with slight variations. Different initial conditions, different physical constants, different outcomes. Entire histories of universes unfolding, ending, and being replaced by new versions, like countless drafts of a story being written and rewritten. From within any one cycle, beings like us would experience a single continuous history, never aware of the many other versions that came before or might follow after. Another gentle but intriguing idea involves limits not of space or energy, but of computation. A simulated universe requires resources in whatever deeper reality hosts it, processing power, memory, structure. If those resources are finite, the simulation might begin to struggle as complexity increases. Galaxies form, life evolves, minds arise, and the informational load grows heavier. Perhaps the universe could begin to slow in subtle ways, physical processes taking longer from an external perspective until eventually the system can no longer keep pace and the simulation grinds to a halt. From inside, this might appear as strange physical anomalies, or it might never be noticed at all if consciousness is tied to the same slowing processes. There's an even more curious thought. What if the simulation has already ended from the outside point of view, but continues to exist as a complete record? Imagine a vast data structure containing the entire history of a universe laid out all at once. Past, present, and future all encoded in a timeless pattern. Within that pattern, conscious experiences are simply parts of the structure, giving the impression of time flowing. From inside, beings would still feel moments passing, choices being made, events unfolding, even though from the outside the computation that generated the structure is finished. In that sense, the universe could be both over and still fully experienced. Whether or not the simulation hypothesis is correct, it encourages us to loosen our grip on the idea that physical reality is the deepest layer of existence. It gently asks what it really means for something to end if what we call reality is itself dependent on something beyond it. Let us drift now toward another strange and beautiful concept that arises from thermodynamics and probability. The idea of Boltzmann brains begins with the notion of a universe in heat death, a vast, cold, dilute expanse where entropy is maximized and organized structures have mostly faded away. Even in such stillness, quantum fluctuations never completely stop. Tiny, random variations in energy continue to occur. Given enough time, these fluctuations can produce almost anything, no matter how unlikely. It is far more probable for a single brain to briefly assemble out of randomness, complete with a flicker of consciousness and false memories, than for an entire structured universe to arise. This leads to a peculiar puzzle. If random conscious observers can appear briefly in a high-entropy universe, then over extremely long times they might outnumber ordinary observers like us, who evolved in stable cosmic environments. That raises the unsettling question of why we find ourselves in a coherent universe with a long, consistent history rather than as isolated flashes of awareness with illusory memories. The puzzle itself suggests that our cosmological models may be incomplete. Yet for our gentle reflection on endings, Boltzmann brains offer a different perspective. Even after stars burn out and galaxies drift apart, existence does not become absolute nothingness. Instead, it becomes a realm of rare, scattered possibilities. Moments of structure emerging from chaos, consciousness flickering on and off like distant fireflies in an endless night. From this viewpoint, heat death is not a final curtain, but a transformation into an unimaginably slow and sparse mode of being. The universe becomes less a stage for ongoing stories and more a background of potential from which brief, isolated experiences occasionally arise. Another doorway into unconventional thinking comes from the holographic principle, an idea inspired by black hole physics and attempts to understand quantum gravity. This principle suggests that the information describing a region of space may be encoded on its boundary, much like a three-dimensional image can be stored on a two-dimensional surface. If this is true in a deep sense, then our familiar three-dimensional world could be understood as a kind of projection emerging from more fundamental information. In such a picture, the end of the universe might not primarily be about matter flying apart or collapsing inward. Instead, it could involve changes in the underlying information structure. Perhaps there is a limit to how much information can be encoded on the cosmic boundary. Perhaps the correlations that give rise to the illusion of continuous space and time could weaken or rearrange. The ending of a universe would then resemble an informational transformation rather than a purely physical event. This connects with a growing tendency in theoretical physics to treat information as more fundamental than matter or energy. Particles and fields may be seen as patterns in a deeper informational substrate. If so, the ultimate fate of the universe might be described in terms of how information is processed, preserved, scrambled, or erased. Maybe the cosmos ends when meaningful information can no longer be maintained, or when quantum processes disperse all structure into noise, or when complexity reaches a maximum and cannot be increased further. Let's now gently touch on the role of consciousness itself. In most scientific frameworks, consciousness is viewed as something that emerges from complex physical systems like brains. It does not shape the basic laws of the universe. Yet some interpretations of quantum theory and some philosophical viewpoints suggest that observers might play a more central role. The participatory anthropic principle proposes that observation is not merely passive, but helps bring definite reality into being. Quantum systems exist in multiple possibilities until measured. Extending this idea in a bold and speculative way, one might imagine that the universe as a whole depends on observation to have definite properties. In such a vision, the end of the universe could be linked to the end of observers. When the last conscious experience fades, perhaps the universe in its definite form fades as well. Or perhaps as long as some form of awareness persists anywhere, reality continues to crystallize into experience moments. This leads naturally to imaginative scenarios about advanced civilizations in the far future. Perhaps intelligence could find ways to endure extreme conditions, existing as subtle patterns of information, or creating new cosmic domains to inhabit, or transforming into forms we can barely conceive. Some thinkers have imagined an omega point, a final state where information processing accelerates toward an ultimate limit, turning the end of physical evolution into a kind of cosmic culmination of awareness. These ideas remain far beyond anything we can test. Still, they serve a gentle purpose. They remind us that our knowledge is partial and evolving. We do not yet understand consciousness. We do not have a complete theory uniting quantum physics and gravity, and we still do not know the true nature of dark matter or dark energy. With so many open questions, humility feels natural. It becomes clear that the real universe may hold endings stranger than any we have described. As we rest with that openness, let us widen our view even further. Everything so far has assumed a single universe whose fate we are tracing. But many modern theories hint that our universe might be just one region within a far larger multiverse. If that is so, the meaning of an ending changes again. The idea of a multiverse arises in several ways. One comes from inflationary cosmology. In many models, the rapid expansion that shaped our early universe does not stop everywhere at once. Instead, it ends in patches, forming bubble universes like ours, while other regions continue inflating. New bubbles keep forming without end. Each bubble may have different physical properties, different constants, different histories. In this picture, our universe is one bubble in an endless cosmic foam. Each bubble has its own beginning and its own end. One might freeze into heat death, another might tear apart, another might collapse. Yet the overall process continues, generating new universes again and again. The question shifts from whether the universe ends to whether our particular universe ends. While the larger multiverse carries on, from a certain perspective, this brings a quiet sense of continuity. Even if our cosmic home eventually grows dark and cold, existence in other forms continues elsewhere. Universes capable of supporting complexity and awareness keep arising. Possibility itself never runs out. String theory offers another route to multiverse thinking. Its mathematics allows for an enormous range of possible configurations, each corresponding to different physical laws. This vast landscape of possibilities might be realized in different regions of a larger reality. Our universe would then be one realization among an immense collection. Endings could involve transitions from one set of physical laws to another, like a shift in the underlying pattern that defines reality. Quantum theory also suggests a kind of multiverse in the many worlds interpretation. Every quantum event with multiple outcomes gives rise to branching histories, all equally real. In this ever-branching structure, some branches might reach cosmic endings while others continue. From the broadest perspective, there are always branches where something is still happening. If any of these multiverse ideas are correct, we can even ask whether the multiverse itself could end. Perhaps the processes that generate new universes could eventually cease. Perhaps all possible configurations could be exhausted. Perhaps a universal transition to a lowest energy state could sweep through every domain of reality. These speculations stretch our imagination to its limits. We do not know if the multiverse exists, and we may never have direct evidence. Yet the concept gently loosens our sense that everything depends on the fate of our own cosmos. It invites us to feel our universe as one expression within a far greater tapestry. In that vastness, endings become local events rather than absolute ones. Even if stars fade here, new stars may be shining elsewhere. Even if life disappears in our region, other forms of life may be awakening in distant domains. There's a quiet poetry in that thought, not personal immortality, but the endurance of creativity itself, patterns forming and dissolving without end. As you rest with these images, imagine an endless ocean of realities, each universe like a bubble rising, shimmering, and gently dissolving, while new bubbles continuously appear. Our universe is one such bubble, precious and temporary, yet part of a boundless process. Holding that vision softly, we can return our attention to our own cosmos with a sense of perspective. Whatever its ultimate fate, it is a chapter in a much larger story. And in the time that remains before any distant ending, there is still complexity, beauty, and awareness unfolding. We have spent so much time imagining the grand and distant endings of the cosmos, the fading of stars, the cooling of space, the slow drift towards silence on scales so vast that numbers themselves begin to feel fragile. But there is another way to look into the future, one that feels at once more intimate and more haunting. Instead of asking only how the universe ends, we can ask how life continues before that ending arrives. We can ask about the fate of complexity, of awareness, of memory, of experience. We can wonder how long organized patterns can resist the universal pull toward disorder, and when the very last thought will flicker into being, when the final moment of consciousness will arise and gently fade. These questions belong to a field with a quietly dramatic name: physical eschatology, the study of the ultimate fate of life and structure in the universe. It is a meeting place of physics and biology, of thermodynamics and imagination, of hard equations and soft philosophical reflection. Here we are not only tracking the motion of galaxies or the decay of particles, we're tracing the possible lifespan of meaning itself. We are asking how long the universe can host not just matter, but experience. Let us begin close to home, on a scale that is enormous by human standards, but still tiny compared to cosmic eternity. The Earth, our cradle and our long companion, is not permanently habitable. The sun is not a static lamp in the sky. It is a star slowly changing as it fuses hydrogen into helium in its core. Over time, this process causes the sun to grow brighter. The increase is gradual, almost imperceptible from century to century, but over hundreds of millions of years, it becomes decisive. In roughly 1 billion years, the sun will shine intensely enough to disrupt the delicate balance that keeps liquid water stable on Earth. The oceans will begin to evaporate more rapidly. Water vapor is a powerful greenhouse gas, so as more of it fills the atmosphere, the planet will trap more heat. This creates a feedback loop. More heat leads to more evaporation, which leads to more trapped heat. Eventually, the oceans may boil away entirely, leaving behind a hot, dry world with a thick, steam-laden atmosphere. Life as we know it, dependent on stable oceans and moderate temperatures, would find no refuge here. And yet, even this dramatic transformation does not have to mark the end of life connected to Earth. If intelligence endures, if technological civilizations survive and continue to develop, there may be ways to adapt. Mars, now cold and thin-aired, could warm as the sun brightens, perhaps becoming temporarily more hospitable. The icy moons of the outer planets might thaw at their surfaces, revealing oceans long hidden beneath frozen crusts. Vast artificial habitats could be constructed, rotating structures in space with controlled environments, independent of any planet. Life might detach itself from the surface of a single world and become something more mobile, more flexible, more at home in the wider solar system. Looking further ahead, we reach a more dramatic phase of the sun's life. In about 5 billion years, it will exhaust the hydrogen in its core and begin to expand into a red giant. Its outer layers will swell outward, potentially engulfing Mercury and Venus, and perhaps even Earth. The inner solar system will be transformed into a furnace. Yet even here, the story of life does not have to end. A sufficiently advanced civilization might have already moved outward, settling in the outer solar system or traveling to other stars. The death of one star, even one as central to our history as the sun, becomes less of a final boundary and more of a milestone on a much longer journey. If travel between stars becomes possible, even at slow speeds over long times, then the lifespan of a single planetary system ceases to define the lifespan of a civilization. There are hundreds of billions of stars in our galaxy, and trillions more in the observable universe. Stars are born, shine, and die over vast ranges of time. The smallest stars, the red dwarfs, burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. A civilization able to migrate from star to star could, in principle, ride this slow parade of stellar lifetimes for an almost unimaginable span. But eventually, even the era of stars comes to an end. In the very distant future, after trillions upon trillions of years, star formation will cease. Existing stars will burn out, cool, or collapse into remnants like white dwarfs, neutron stars, and black holes. The universe will enter a long twilight in which new light is rare and old light is fading. It is here in this deep future that thinkers have begun to ask how intelligence and organized complexity might adapt. One of the most evocative explorations of this question came from the physicist Freeman Dyson. He asked whether life could persist indefinitely in an ever-expanding, ever-cooling universe. His answer was not based on biological bodies like ours, but on the possibility of minds that change their pace. As the universe cools, energy becomes more scarce and more diffuse. Any process that uses energy must slow down if it is to continue for a very long time. Dyson imagined civilizations that enter long periods of dormancy, lowering their energy consumption almost to zero, then waking briefly to think, to remember, to observe, before sleeping again for even longer stretches. From the outside, such a civilization would appear almost frozen, with bursts of activity separated by eons of stillness. But from the inside, if subjective experience only occurs during the active phases, consciousness might feel continuous. A thought, then a long sleep that is not experienced, then another thought. In this way, a finite store of energy could in principle support an infinite sequence of conscious moments, spaced ever farther apart in physical time. There is something strangely beautiful in this image. Consciousness becomes like a series of sparks in an immense darkness, brief illuminations separated by vast stretches of quiet. The universe grows colder and emptier, Yet awareness does not vanish. It simply slows, adapts, becomes more patient than we can easily imagine. Other speculations go even further from familiar biology. Advanced civilizations might no longer be made of cells or tissues at all. They could be patterns encoded in stable configurations of matter, perhaps at atomic or subatomic scales. They might use reversible computing, minimizing energy loss, stretching every available gradient for as long as possible. Information, rather than flesh, becomes the core of identity. Memory and processing replace metabolism and growth. Black holes, often seen as symbols of cosmic destruction, may in this far future become centers of possibility. A rotating black hole drags space-time around with it, creating a region outside the event horizon where energy can, in theory, be extracted. This process, known in physics, suggests that a black hole is not just a sink, but also a potential source. An advanced civilization might orbit such an object, drawing on its rotational energy. In a universe where stars are gone, a spinning black hole could be one of the last reliable energy reservoirs. Around these dark giants, life would unfold in an environment utterly unlike anything we know. The background universe would be almost completely dark, the glow of ancient starlight long redshifted into faint whispers of radiation. The black hole itself would dominate the sky, a sphere of darkness bending light into strange arcs. Energy would be precious. Every computation, every act of memory, every flicker of thought would be carefully budgeted. This era, sometimes called the black hole era, could last for astonishing lengths of time. Black holes slowly lose mass through a process known as Hawking radiation, an almost imperceptible trickle of particles that, over unimaginable spans, causes them to evaporate. The larger the black hole, the longer it lives. Some could persist for periods so vast that our current age of the universe seems like a brief flash by comparison. Civilizations living in orbit around black holes would face a slow decline. As the black hole radiates away its mass, the available energy decreases. They would have to become ever more efficient, ever more sparse in their use of power. Perhaps their subjective lives would stretch further and further apart, each moment of awareness separated by longer ages of stillness. Eventually, the black hole would shrink to the point where its final evaporation becomes a burst of radiation. That last flash might be both an ending and an opportunity, a final release of energy that could be used in one last act of computation, one last experience, one last thought. There is something deeply moving in these images of persistence. They show complexity not as fragile, but as adaptable, capable of transforming itself again and again to match the changing conditions of the cosmos. Consciousness, in these visions, is not tied to a single form or environment. It is a pattern that can migrate, slow down, compress, and reconfigure itself in order to endure. And yet, even these heroic scenarios seem to run into a wall. In the standard picture of heat death, the universe approaches a state where energy is evenly spread, where there are no gradients left to exploit, no differences in temperature or density that can drive processes. Without gradients, no work can be done. Without work, no computation, no metabolism, no change. The universe becomes a vast equilibrium, silent and unchanging. In that limit, it is hard to see how any form of life or mind, however exotic, could continue. Every strategy only delays the inevitable. The last black hole evaporates. The last useful energy difference is exhausted. The last organized process winds down. If this picture is correct, then there really is a final moment of experience, a last instance of awareness somewhere in the cosmos, after which there's only stillness. Unless, of course, our understanding is incomplete. It often is. There may be physical processes we do not yet know, ways in which information and structure can persist even in conditions that seem uniform to us. There may be deeper layers of reality, new phases of matter, or connections between universes that allow for escape from what we currently see as final limits. These possibilities are speculative, but so were many ideas in physics before they were understood. Beyond the physics, there's a psychological and philosophical layer to these speculations. When we imagine civilizations struggling to survive until the last possible moment, we are also expressing something about ourselves. We reveal a desire for continuity, for experience to not simply vanish, for meaning to have a chance to stretch as far as it can. These cosmic futures are mirrors in which we see our own hopes and fears reflected on a grand scale. There's also the question of what such long-lived civilizations would do. Imagine a society that knows it has trillions upon trillions of years ahead, though with ever-decreasing energy. What projects would it pursue? Perhaps it would turn to knowledge, attempting to understand every aspect of physics, every mathematical truth, every possible pattern that can exist. It might run simulations of entire universes, exploring what could have been or what might be possible under different laws. Art might also evolve in ways we can barely imagine, using time itself as a medium, creating experiences that unfold over millions of years. Philosophy could become an active exploration of possible modes of being, testing different ways of structuring consciousness and value. With external novelty fading, inner landscapes might become the main frontier, vast worlds of thought and imagination. Or perhaps, in a very far future, the emphasis would shift from doing to simply being. When almost everything that can be explored has been explored, when most questions have been answered or transformed, there might arise a quiet acceptance. The last civilizations might not rage against the dying of the light, but instead witness it with a kind of reverence. They would be the universe becoming aware of its own fading, the final observers of a story that has lasted beyond measure. There's a gentle poignancy in that idea. Consciousness arises from the cosmos, evolves, learns, and eventually watches the conditions that made it possible slip away. In its final acts, awareness might not try to conquer entropy, but simply to understand, to appreciate, to say a kind of farewell. From the perspective of infinity, whether life lasts another billion years or another number, so large it defies comprehension, may not matter. Any finite span, no matter how long, is small compared to eternity. What gives value to experience is not its duration, but its presence. A single moment of awareness, of love, of understanding, has a quality that is not measured only in time. So when we imagine the far future of life, we are not only tracing possible survival strategies, we're also being invited back to the present. Right now, in this brief era when stars shine brightly and planets are warm and minds are active, consciousness is abundant. The universe is in a phase where complexity can flourish. We are part of that flourishing. The fact that there may one day be a last thought does not diminish the thoughts happening now. If anything, it gives them a quiet intensity. Every experience is a rare event in the long history of matter. Every moment of awareness is the universe briefly knowing itself. As we gently hold these vast futures in mind, we can feel both the fragility and the resilience of life. We can sense how small we are in time and space, And yet how extraordinary it is that anything like thought exists at all. The story of life in the cosmos may be long or short on cosmic scales, but is real wherever and whenever it unfolds. And so, rather than ending in despair, this contemplation can soften into wonder. The future may hold migrations between stars, minds that sleep for eons, civilizations orbiting black holes, and finally a slow fading into stillness. Or it may hold surprises beyond anything we can currently imagine. Either way, the present moment remains luminous. Here now, complexity lives. Here now, consciousness asks questions about its own fate. In that simple fact, there's a quiet kind of miracle, one that does not depend on lasting forever, but on being even briefly at all. We have traveled through many scientific possibilities for how the universe might end, from slow fading futures to sudden and dramatic transformations. Now, as we move into a more reflective space, it is worth exploring what these distant cosmic endings mean for us, not only as physical beings living on a small planet, but as conscious creatures who search for meaning, purpose, and understanding. When we hear that the universe may one day fall silent in a heat death, or be torn apart in a big rip, or transformed by a vacuum decay, it can feel unsettling. These scenarios stretch far beyond human timescales, yet they quietly challenge some of our deepest assumptions. If everything eventually disappears, if every star burns out and every structure dissolves, we are naturally led to wonder what that says about the value of anything we do. For many people, the first reaction is to connect meaning with permanence. We're used to thinking that something matters more if it lasts. A monument feels important because it stands for centuries. A tradition feels meaningful because it is passed down through generations. So when we project our thoughts forward into a future where nothing at all remains, it can seem as if meaning itself begins to evaporate. But this connection between meaning and eternity is not as solid as it first appears. In our everyday lives, we constantly experience things that are deeply meaningful even though they are brief. A conversation that lasts an hour can change a life. A piece of music that plays for a few minutes can stay in memory for decades. A single moment of kindness can echo through a person's inner world long after the event itself has passed. We do not usually dismiss these experiences as meaningless simply because they are temporary. In fact, their fleeting nature is often part of what gives them their emotional power. A sunset is beautiful partly because it fades. A season is precious partly because it does not stay. Our own lives feel vivid and urgent partly because we know they are limited. From this perspective, the eventual end of the universe is not a negation of meaning, but an extension of a pattern that is already present everywhere. Impermanence is not an exception in reality, it is the rule. Stars are born and die. Galaxies form and collide. Species emerge and vanish. Civilizations rise and fall. Change is not a flaw in the system, it is the system. Many philosophical and spiritual traditions have recognized this. They suggest that suffering often comes from trying to hold on to what cannot be held, from demanding stability in a world that is fundamentally fluid. When we insist that things must last forever in order to matter, we set ourselves up for disappointment, because forever is not a feature of the physical universe as far as we can tell. Seen in this light, the cosmic ending is not a special catastrophe waiting at the end of time. It is simply the largest scale expression of a process that is always happening. The same principle that causes a flower to wilt and a memory to fade also governs the lives of stars and the fate of galaxies. Everything participates in this great flow of arising and passing away. There can be something strangely freeing in fully accepting this. If nothing is required to last forever, then we are released from an impossible standard. We do not have to build something eternal in order for our efforts to be worthwhile. We do not have to leave a permanent mark on the universe for our lives to have depth and significance. Meaning can live entirely within the span of an experience itself. There's also another way to think about persistence that does not depend on physical survival. Even if all structures eventually dissolve, it will still be true that they existed. It will still be true that stars once shone, that planets once formed, that life once emerged, that minds once wondered about their own existence. The fact that something happened is not erased by the fact that it no longer continues. Some thinkers have suggested that information may be more fundamental than matter and energy. In this view, what we call physical objects are patterns of information arranged in particular ways. If that is so, then perhaps what truly persists is not the material form, but the informational structure, the fact that a certain pattern unfolded in the history of reality. Even if the universe reaches a final state where no further events can occur, the entire story that led to that state remains part of the structure of what is. The existence of every moment, every life, every thought becomes part of the complete description of reality. Nothing needs to be remembered by a future observer in order to have been real. Its reality is contained in the fact that it occurred at all. Another perspective opens up when we consider the possibility that our universe is not the only one. Some cosmological theories suggest a vast multiverse, an enormous landscape of different regions with different conditions, perhaps even different physical laws. In such a picture, the end of our universe is not the end of all existence, but one event among countless others. This idea can feel comforting because it suggests that existence in some form continues even if our local cosmic story comes to a close. At the same time, it can feel disorienting. If there are infinitely many worlds, each with their own histories, then our particular universe may seem small and easily replaced. It can appear as though nothing here truly matters because there are endless variations elsewhere. Yet this conclusion does not necessarily follow. The presence of many other stories does not erase the reality of this one. The fact that there are billions of human lives does not make any individual life meaningless from the inside. Each conscious perspective is unique. Each moment of awareness is a singular event in the unfolding of reality, never to be repeated in exactly the same way. From within a life, from within a moment of experience, the scale of the multiverse does not reduce the immediacy of what is felt and known. Joy still feels like joy. Pain still feels like pain. Love still feels like love. The local reality of experience remains vivid and significant regardless of how many other realities may exist beyond our horizon. Thinking about the end of the universe also raises ethical questions. If everything eventually disappears, does that mean our long-term actions do not matter? If humanity will one day vanish along with the stars, why care about the distant future at all? Why worry about future generations if all generations are temporary in the grand cosmic view? Most ethical frameworks would answer that temporariness does not cancel responsibility. The fact that a life is finite does not mean suffering within that life is unimportant. The fact that a civilization will not last forever does not mean its flourishing or its collapse is irrelevant. Value exists within time, not only outside it. We still have reasons to reduce suffering, to cultivate beauty, to seek knowledge, and to build more just and compassionate societies, because these things shape the lived experiences of conscious beings. Even if those beings are temporary, their experiences are real while they occur. A future that contains less pain and more well-being is still preferable to one filled with misery, even if both futures are finite. It is also important to remember that cosmic endings lie on timescales so vast that they're almost meaningless for practical human concerns. The difference between a universe that lasts 1 trillion years and one that lasts 10 trillion years does not change the urgency of how we treat each other now, or how we care for the fragile biosphere that supports us. Our ethical horizon is shaped by the foreseeable future, not by the final fate of space-time. There is a contemplative dimension to all of this as well. Many reflective practices invite us to consider our own mortality, not as a source of fear, but as a way of clarifying what truly matters. When we remember that our time is limited, trivial worries can lose some of their grip, and deeper values can come into focus. Contemplating the mortality of the universe works in a similar way, but on a grander scale. It reminds us that nothing we see is fixed or guaranteed. The stars above us, which seem so steady and eternal, are themselves temporary lights in a long cosmic night. This realization can soften our attachment to rigid expectations about how things must be. Paradoxically, accepting impermanence often deepens our appreciation of the present. When we truly feel that this moment is unrepeatable, that this exact arrangement of thoughts, sensations, and surroundings will never occur again, it can bring a quiet intensity to experience. Ordinary things can appear more vivid, more worthy of attention, simply because they are not permanent. There is also a humbling aspect to the cosmic perspective. On the scale of galaxies and eons, human concerns can seem very small. Our conflicts, ambitions, and anxieties shrink when placed against the backdrop of billions of years and billions of stars. This could be a relief. Not every mistake is a cosmic tragedy. Not every problem is of ultimate importance. At the same time, we are not separate from this vast universe. We are expressions of it. The atoms in our bodies were forged in ancient stars. The laws that govern distant galaxies also govern the neurons in our brains. When we think about the cosmos, it is the cosmos thinking about itself through a particular arrangement of matter and energy. Consciousness adds a unique dimension to the story of the universe. Without conscious beings, events would still occur, stars would still burn, and galaxies would still spin, but there would be no experience of these processes. There would be no wonder, no curiosity, no sense of beauty or mystery. Through conscious life, the universe becomes not only a collection of events, but a field of lived experience. For a brief period in cosmic history, in scattered places, matter organizes itself into forms that can ask questions about existence. That alone is extraordinary. Even if this phase is temporary, even if it occupies only a tiny fraction of the universe's lifespan, it is still a real and remarkable chapter in the overall story. When we think about the end of the universe, we're also thinking about the end of this chapter of conscious experience, at least in our region of reality. That can feel poignant, but poignancy is not the same as meaninglessness. A story does not lose its value because it has an ending. In many cases, the ending is what gives the story its shape and emotional depth. Perhaps the wisdom suggested by the cosmic view is similar to the wisdom suggested by our own mortality. We cannot hold on to everything. We cannot make any moment last forever. What we can do is participate fully while we are here. We can pay attention. We can care. We can create pockets of understanding and kindness within the brief window that is open to us. The universe will one day change beyond recognition. Stars will fade. Structures will dissolve. The conditions that allow life and mind to exist will eventually pass. Yet right now, in this moment, the universe is vibrant. Light travels across space. Planets circle their stars. Life breathes and grows. Minds reflect on their own place in the whole. You're a part of this ongoing process. You are one of the ways the universe is aware of itself, here and now. That fact does not need to be eternal in order to be meaningful. It is enough that it is real in this moment, that experience is happening, that understanding is possible. Let this awareness settle gently, not as a heavy thought about endings, but as a quiet appreciation of presence. The vast story of the cosmos includes birth and death, formation and dissolution, beginnings and endings. Within that immense flow, this moment exists, and you are here to witness it. We have traveled together across unimaginable distances through billions of years of cosmic history, and in a future so remote that the human mind can barely hold them. We have explored slow endings and sudden ones, gentle fading and violent transformation. We have stood at the edge of heat death, where the universe thins into darkness and silence. We have imagined the Big Rip, where space itself tears everything apart. We have considered cycles of death and rebirth, and the strange possibility that a tiny quantum event could one day rewrite the laws of reality in an instant. And now, as this long journey of thought comes to a close, what remains with us is not a single answer, but a deep and honest uncertainty. For all our equations, for all our telescopes and satellites, for all the brilliance of human curiosity, we still do not know with certainty how the universe will end. We have powerful models. We have evidence that points in certain directions. We have constraints, probabilities, and theories that fit the data we have. But the final fate of everything, the true long-term story of the cosmos, remains open. There is something profoundly fitting about this. The universe has always been larger, stranger, and more subtle than we first imagined. Again and again, just when we thought we had reached a stable understanding, reality surprised us. There was a time when we believed the universe was eternal and unchanging. Then we discovered cosmic expansion. There was a time when we thought ordinary matter made up everything. Then we uncovered dark matter and dark energy. Each generation of science opens new windows, and beyond each window lies a wider mystery. It is entirely possible that future discoveries will reshape our picture of cosmic destiny just as dramatically. We may learn that dark energy is not constant, that it evolves in ways that lead to a far more dynamic future. We may find subtle patterns in the cosmic background radiation that hint at events before the Big Bang, or at cycles of universes before our own. A successful theory of quantum gravity might reveal that space-time itself has phases, transitions, and behaviors we have not yet imagined. Or the future may hold something completely unexpected, an idea so far outside our current frameworks that we do not even have a language for it yet. This is not a failure of science. It is a sign of its honesty. Science does not promise final answers carved in stone. It offers a method, a way of continually refining our understanding, always open to revision in the light of new evidence. There's a quiet humility in this stance, and also a quiet beauty. We are participants in a vast, unfolding mystery, not masters standing outside it. Our knowledge grows, but it always floats in an ocean of the unknown. When we contemplate the end of the universe, We are looking toward a horizon that may forever recede as our understanding deepens. Yet even without certainty, the exploration itself has meaning. By thinking about how the universe might end, we have learned how it works now. We have seen how the laws of thermodynamics shape the flow of energy in the arrow of time. We have glimpsed the strange flexibility of quantum fields, where even empty space is alive with possibility. We have understood how gravity sculpts structure, how expansion stretches the cosmic fabric, how delicate balances determine whether things clump together or drift apart. In stretching our minds toward these immense futures, we have also stretched our sense of scale. Human life, so vivid and immediate, unfolds over decades. Civilizations span centuries. Recorded history covers only a few thousand years. Against this, the life of stars lasts billions of years, and the future of the cosmos may extend trillions upon trillions of years beyond that. Contemplating such scales can feel dizzying, but it can also be strangely calming. Our worries, our deadlines, our daily frustrations soften a little when placed against the vast backdrop of cosmic time. We have also seen that cosmic endings are not punishments or failures. They are not the result of something going wrong. They follow naturally from the same laws that allow stars to shine and life to evolve. Entropy increases. Energy spreads out. Structures form, persist for a while, and then dissolve. The end of the universe, in any of the scenarios we discussed, is not an act of cruelty. It is simply the continuation of processes that have been at work since the beginning. There could be deep peace in recognizing this. Impermanence is not an exception in reality. It is its fundamental rhythm. Every breath you take arises and passes. Every thought appears and fades. Every star ignites and eventually cools. The universe itself participates in this rhythm, expanding, evolving, and one day transforming into something simpler and quieter. This impermanence is not a flaw in existence. It is what makes change possible. Without change, there would be no motion, no growth, no evolution, no experience. A perfectly static universe would contain no stories at all. Because things do not last forever, events can unfold. Because structures eventually dissolve, new structures can arise. Because moments pass, time has meaning. Right now, you find yourself in a very special era of cosmic history. The universe is about 13.8 billion years old enough for generations of stars to have lived and died, enriching space with the elements needed for planets and life. Yet it is still young enough that stars shine brightly in great numbers. Galaxies are rich with structure, and the conditions for complexity are widespread. You live in a window of time when the universe is active, luminous, and capable of supporting minds that can reflect on their own existence. This era will not last forever. Star formation will slow. Galaxies will drift farther apart. The sky of the distant future will be darker and emptier than the one we see today. But that only makes the present more remarkable. You are here during a chapter when the cosmos is vibrant with light and possibility. You are part of the brief flowering of complexity in an otherwise vast and mostly silent expanse. Your life, too, is a brief flowering. From the perspective of atoms, you are a temporary pattern, a dynamic arrangement that holds together for a while and then returns to the wider cycles of matter and energy. If from the inside, your life is not a pattern, it is a stream of experiences, feelings, thoughts, relationships, and moments of awareness. It is rich, textured, and meaningful from within. Contemplating the end of the universe can bring a gentle shift in how we hold all of this. It can remind us that we do not need forever in order to matter. A song does not need to last for hours to be beautiful. A story does not need to have an infinite number of pages to be worthwhile. A life does not need to be eternal to be full of meaning. In fact, knowing that things are temporary often sharpens our appreciation. When you watch a sunset, part of its beauty comes from the knowledge that the colors will fade. When you share time with someone you love, part of the tenderness comes from the awareness that time is limited. Impermanence gives edges to experience, and those edges give it depth. As this reflection comes to a close, you are invited to shift from vast abstractions back to the simplicity of the present moment. Feel the weight of your body supported by whatever holds you. Notice the gentle movement of your breath, the quiet rise and fall that has been with you since the beginning of your life. Around you, countless processes are unfolding in your cells, in the air, in the wider world, all part of the same universe whose distant fate we have been imagining. The ultimate ending of the cosmos lies so far ahead that it has no practical claim on this moment. What exists now is life, awareness, sensation, and a subtle miracle that something rather than nothing is being experienced. You are a small but genuine expression of the universe, a place where matter has become mindful, where the cosmos reflects on itself. Let that be enough. Let uncertainty remain without needing to be solved. Let impermanence be present without turning into fear. Rest in the fact that right now, in this brief and luminous interval of cosmic history, you are here. You are breathing. You are aware. The universe will continue its vast unfolding. Stars will be born and will die. Galaxies will drift and change. Laws we only partly understand will guide transformations on scales beyond imagination. And within all of that, there is this quiet moment, this simple experience of being. Stay with that for a while. Let the grand questions soften at the edges. Let the need for final answers loosen. There is a gentle completeness in simply being a conscious part of the whole, however temporary, however small. The universe may end one day, in fire or in ice, in silence or in sudden change. But this moment is not the end. This moment is alive. And in this living moment, the vast cosmos has, for a little while, opened its eyes through you.